Please go ahead.
Okay, today we should discuss how physics is implemented inside G4. It is particle and process interfaces. We have several topics for today. G4 basic interfaces to physics, particles, processes, physics list, ion and exotic particles, and G4 cards. I will do a short pause after each of these topics, so you may ask a question online. If it will be needed, please ask. G4 basic interface to physics. It is important that this interface is abstract, and there are base physics abstract classes, G4 particle definition, G4VProcess, G4ProcessManager. Particle definition shared between threads. G4VProcess is thread local, and G4ProcessManager is also thread local. Configuration of physics is prepared in mandatory class G4V user physics list. These interfaces, which I described above, are very stable. From the beginning of G4, they allow users to work with different G4 versions and provide basis for a new development. Concrete physics is implemented in physics models and cross-section classes. Alternative models and cross-sections are provided in G4 library, but any user may add a custom particle or custom process or custom physics model or cross-section. Let's discuss G4 particles. G4 particle definition class is the main object keeping static information. It is, of course, name of particle, mass, charge, quantum numbers, decay table. These parameters of particles are not changed during the run. They are absolutely stable, and they are shared between all threads in multi-threaded mode. In G4 notation, we have so-called stable particles. For example, leptons, electron, positron, muons. They are not, except electrons, they are not stable. They have, let's say, final time, and they interact with matter or decay. But nevertheless, in our notation, they are stable. There are bosons, G4 gamma, G4 optical photon. From physical point of view, it is electromagnetic wave with, there is no strong boundary for wavelength between gamma and optical photons. But we use them differently because G4 gamma, it is a particle which take interactions with matter, allowed to produce secondary particles in gamma, interaction with material, with atoms. And optical photon has specific processes like reflection, refraction, and the optical photon transport is completely different from G4 gamma transport. So being the same, they are different in names and different for configurations which we apply on these particles. We have also a fake particle, geantino. it is a particle without any interaction. It may be used for ray tracing for some tests, but of course not for final simulation, which you want to do when you want to have a physics result. There are so-called stable hadrons, pions, kaons, and other, which in reality are not stable. They have lifetime. And there are light ions, like deuteron, triton, helium-3, alpha particles, and their anti-light ions. We have 12 hyper and anti-hyper nuclei, which are added recently to Gen4. We also have G4 generic ion, which is used to define physics for all other ions. Variants of ions are too many, so we use this object G4 generic ion to describe all the rest. Short-lived hadrons normally do not track by Gen4, but used internally by hadronic models. So we have quarks, d-quark. We do not track quarks in Gen4 tracking because they are not going through normal material, but all what happens inside very short distances. There may be resonances like light resonances, omega and rho, or other resonances, which have very short lifetime, which is shorter than life than relativistic particle comes through nuclei. Everything happens within nucleus, and nothing is going out. So it is only for hadronic models, not for tracking. Because for us, multi-threaded mode is important. We need to speak about some details. It is split classes which we have in order to handle multi-threaded physics. There are static quantities, which, as we discussed before, were defined in particle definition. They are shared. So on left part of this cartoon, there's a particle definition with mass, charge, lifetime, decay table, and it is unchanged and is seen by all classes of Gen4, may be seen. On other part of cartoon on the right bottom, there is a red square. It is a list of processes. Physics process by design are thread local. It means that the same similar objects are in each thread. Why processes are only defined per thread? Because when we transport a particle, process may have a catch, and its state may be changed on next step, and it is not stable. Process may be shared between different particles. So we need to keep in each thread its own copy of process. And in the middle of this cartoon, there is a class which is process manager. Process manager has a possibility using splitting mechanism be accessed from particle definition and know the list of processes in each thread. And for that, particle definition splitter is used for this process manager to perform this function. Any questions? If not immediate, let's go to G4 processes. We have classification of G4 processes. Each process is a class. It may be electromagnetic, hadronic, decay, parameterized, and even transportation. And maybe different. Any process has two characteristics, type and subtype. Type is string. It may be electromagnetic, hadronic, or whatever. And subtype is integer. We strongly recommend to use subtype of process if you design in your simulation Monte Carlo truth. So history of what happens with particles inside your setup. Because handling of integer values is faster than strings. The list of subtypes is stable since it was introduced. With time, we add extra subtypes, but we never change and we never delete. We never change what is already in previous versions of G4. We only add extra subtypes if a new process appears, and we include new process in G4 distribution. Any process may be initialized before start of run. For that, there are methods. Is applicable. So process should check the particle definition and say true or false. By default, in all cases, it is true. Prepare physics tables. Prepare physics table also depend on particle definition. This step is needed in order to prepare initialization of physics. For example, physics values may be, after tables are prepared, may be download from disk and not recomputed. And build physics table is next call, which called for all physics processes at initialization. It is assumed that after build physics table, each process is ready for work. How we go from G4 track to processes? We have a G4 track object, which we need to propagate in some setup in your, for example, detector or your experiment, where we take this track and trying to do propagation. Track consists of two components: dynamic particle, which has information about current momentum, preassigned decay, and this dynamic information may be changed after each step of particle. And particle definition, it is static fixed parameters of a given particle. Particle definition has access to process manager and hold pointers to physics processes. And in this scheme, when we propagate track through material, we know everything in physics. We know what type of particle we have. We know which physics processes may happen. This upper part is handled by a kernel. Kernel does not know type of processes, do not know details. It take abstractly a track and propagate it through geometry. A low part below this dot line, red dot line, is a part where a real physics is defined. And this should be defined before start of run. Before start of run, each particle definition should know what physics may happen with this particle. Few words about different kind of physics. Electromagnetic. It is quite a big, let's say, diverse library, which has so-called standard part. It is a complete set of electromagnetic interactions, means process classes for charged particles and gammas, which are applicable roughly from 1 keV to few PeV. And of course, this physics should be used in each kind of G4 application. There is low energy EM part, which not used in all applications, but it includes special treatment of low energy electrons, positrons, gamma, and charged hadrons. It is more sophisticated approximation, which takes into account atomic shell structure and other things, even may take into account molecular structure or crystal structure. Some of these models are even valid down to 10 electron volts. But those who work at very low energy cannot cannot be used for high energy, depending on particle type. For example, for electrons, currently it is 1 MeV. For proton or alpha particle, it's 300 MeV. There are optical photon interactions which belong to electromagnetic physics in our notation. And it includes reflection, refraction, absorption, wavelengths, shifting, Rayleigh scattering, and optical photon is the particle type. We have also one implementation on phonon physics in crystals. We know that this is also possible. Hadronic physics. Pure hadronic interactions in G4 are implemented in energy interval from 0 to 100 TeV. It includes elastic, inelastic, capture, fission processes. There is a radiative decay, both AtRest and slide, with which use all known data of radiative transitions. Photonuclear interaction from about 1 MeV to 100 TeV, leptonuclear interactions from approximately 100 MeV to 100 TeV, which include electron-positron nuclear reaction and muon nuclear reaction. We also have variants of neutrino nuclear interactions. Decay processes include weak decays, leptonic, semi-leptonic, and also radiative decay of nuclei, beta decay, for example. Electromagnetic decay, like pi 0 into 2 gamma. Strong decay, not included by default in this list. They very often are part of hadronic models, and they may be assigned by user to a particle, especially if we speak about so-called short-lived hadrons. Of course, all possible reaction channels should be included inside model which use these intermediate objects in the simulation. We have so-called parameterized process, which may be, of course, maybe not only for hadronic physics, but maybe for electromagnetic physics, whatever physics processes. What means parameterized? It is assigned to G4 logical volume. Instead, step-by-step simulation, it takes over all particles which enter this volume and produce final hits in this logical volume. It may be part of fast simulation, but at the same time, it may be part of slow simulation. Inside this logical volume, you may implement all type of physics interaction, but you return to G4 hits and the list of particles which are leaving from this volume. But you are free to do whatever you want inside. For examples, G4 shower generation may be substituted by fast sim parameterization. But we also have another example where transport in bending crystals are implemented inside this bending crystal. Physics is different from physics with ordinary amorphous materials. So this type of physics may be implemented within G4 framework. Transportation process responsible for propagation of particles in geometry, in electromagnetic or gravitational field, and need to be assigned to all particles which we transport. So the difference between short-lived and all other particles is in the fact that so-called stable particles can be transported, while short-lived, which are within nuclei, they are not transported by G4 transportation. How G4 tracking is performed? Track is the main object which we transport through geometry, and this transportation performed step by step. And we have not only object G4 track, but also object G4 step. And G4 step knows about beginning of end of track. Track may be stopped due to many reasons. For example, physics interaction. When we produce secondary particles, secondary tracks. Or it may be stopped when track enter geometry boundary between two volumes. In G4, normally, we have to stop a track and boundary. In that case, logic of all transport is correct, because in next volume, we may have different density, different material composition. So cross-sections of all processes will be different. We need, in new volume, we need to understand what cross-sections are. And then we continue step-by-step simulation within next volume until we enter end of the next volume and will be transformed to another one. Step length is a result of competition of all involved processes which propose step length, and the minimal value of step length is taken. There are different kinds of processes. There are processes which define, for example, step limits. They don't want that step is too big. They ask for shorter step lengths in order to correctly handle your interaction. And another part, which is a random step length for the next interaction. So this combination of different step limits which come out from physics processes which define each new step. And when we start from one point, we make a step. In the next step, we may have different energy. We may have different direction. We may have different polarization of a particle. And even some dynamic properties of particles may be changed. A few words about G4 process actions. As we discussed before, G4V process is an abstract class defining all physics. And in this abstract class, there are a number of interfaces. And there are interfaces which correspond to actions. AtRest action may be applied for decay, for example, or for positron annihilation when a particle cannot move anymore. It has zero kinetic energy and is somewhere inside matter. Of course, it is never stop, we know, but it is our step-by-step procedure assume that a final particle may have zero kinetic energy. But there are another actions, another type of actions, AlongStep. During the step, there may be interactions. For example, low energy particles are produced due to ionization, or Cherenkov may produce Cherenkov radiation, or whatever. All these secondary particles produced AlongStep. But there is also PostStep possibility. When step is stopped, it is possible to have interaction. It may be decay, it may be electromagnetic interaction, it may be hadronic interaction, and secondary particles are produced. In G4 logic, we produce secondary particles, AlongStep, PostStep, and even AtRest, and we take produced G4 tracks and put in stack. And this stack will be used for further simulation of transport within your system. There are virtual actions which are implemented in for all processes. AtRest get physics interaction length. AtRest do it. AlongStep get physics interaction length. AlongStep do it. PostStep get physics interaction length. PostStep do it. In case of AtRest, no length can be provided via AtRest, but we may provide a time. So method is called get physical interaction length, but in reality it is time for the phase process, which will happen with this particle which is stopped. So before step, all processes say what is expected physical interaction length for this process. Then G4 kernel make a decision which step length should be taken and make a step. And when step is done, depending whether it is AtRest or it is only AlongStep or it is also PostStep, do-it methods are called. So it might be AtRest, AlongStep or PostStep, and secondary particles may be produced in this approach. If you prepare your own physics process, new process, you should not also forget about existence of extra runtime virtual methods, which may be useful, but not mandatory to be implemented. It is called start tracking. When you take a track and decide to track it, you call start tracking method. And also end tracking for a given G4 track. You may implement this method as well. By default, these two methods do nothing. So we can have more complex processes which has component AtRest and PostStep, AlongStep and PostStep. For example, decay may happen both AtRest and PostStep. If you implement your own process, you may use inheritance not from G4V process, but from combined like G4V discrete process, which is only PostStep. G4 continuous discrete process, it is AlongStep and PostStep. Of course, majority of processes are discrete because they happen PostStep, but there are, for example, energy loss processes which happens AlongStep. There are energy loss at step and maybe, for example, delta electron or Bremsstrahlung produced PostStep at point or at PostStep point. For electromagnetic physics, there are extra additionally to G4 V discrete process. There is G4V EM process, G4V energy loss process, and G4V multiple scattering. For hadronic processes, there are extensions G4 hadronic process, G4 hadron elastic process. Process manager. Process manager should be able to work with all complications which I described in previous slides. And it has to maintain vectors of actions. And this is actions at rest, AlongStep, PostStep, and the process manager help G4 kernel to decide what to do with given track, how long is current step, and what should be done at a step. There are few critical points which you should be aware. Multiple scattering process. It is very important process which was introduced in previous century. It was shown that many elastic scattering can be described as one scattering which takes into account this multiple elastic process. And this was together with ionization process, it was a base so-called condensed history approach, when it is allowed to make a step, macroscopic step for any particle, and it allows to have performant simulation. Basically, when we introduce ionization and multiple scattering, we introduce a possibility to do simulation faster. But there is a drawback of this, because one needs to use these processes accurately, because multiple scattering can shift at point of a step. If you have many elastic scattering on a track of a particle, it is possible that the end point at given step is slightly shifted. And this somehow should collaborate with transportation process. Because if due to multiple scattering, for example, you may never pass geometry boundary. You need to avoid this. Another important thing is that scintillation, Cherenkov, other processes, when you implement this, you need to be sure that all other processes are already called, and you know initial, final kinetic energy of a particle at the step, and you know exactly trajectory. Then you may implement at a step scintillations and Cherenkov radiation, and maybe some other radiation. So there are processes which can be called only if we know everything about the step. Some time ago, maybe I expect 15, maybe more years ago, we introduced physicalist helper class, which keep information about process ordering. And if you combine your own physics list, then you may use it. In physics list, which we broadcast with G4 distribution, physics list helper is used everywhere, more or less everywhere. Few illustration about process ordering. So the most strong rule for multiple scattering transportation, and you need to use correct order of processes. For charged particles, you get AlongStep physics interaction lengths in some order, where the last is transportation and second before the last is multiple scattering. Why we need to do this? Process return through step lengths, and multiple scattering take into account that real length due to multiple scattering is larger than distance between 2 points, because trajectory due to several elastic scattering is not straight line. So for physics, if we know cross-section, we know distance to the distance along the track when physics process will occur. And this trajectory is not straight line. By using such order, we may take this into account. But transportation is the last. So we propose this point, and it turned out that our endpoint is within next geometry object. Here is a green box. So we decide that it is not what we have to do. We decide that our step should be shorter and should stop at boundary. The question is, it is not enough. We need now to sorry, it's run away. So we need to take corrections at this point. And we need to take into account that new interaction, new real length of a track is larger than straight distance from initial point to boundary. By the way, multiple scattering in case of reaching this boundary is not used. The last step before the boundary do not involve lateral displacement of endpoint. We cannot simply do it because then tracking will never converge. And more or less reasonable tracking is achieved in this order of processes when step limit is defined by physics processes and multiple scatterings and transportation. But when we ask do it actions, everything will be in different order. First, transportation will transport particle to given point, then multiple scattering will change direction of our track, and then all active processes will be called. When a track may be created, there are two possibilities. Track may be created by using primary generator action. So in the beginning of a given event, the number of primary particles are created, and then they are transported through your setup. Or maybe G4V process. So any physics process may provide a list of secondaries if this process is chosen as process, interaction of which is chosen at given step. How long we should transport this track in the setup? There may be circumstances. Transport out of the world volume. In that case, we need to kill a track. Inelastic interaction, when particle disappears and secondaries are produced. Decay. Again, particle decay and new particles are produced as a result of decay. If we apply so-called tracking low energy cut, we may decide to kill given track if energy is too low. For neutrons, we may apply so-called neutron killer. And the user can add to the list of processes so-called G4 user limits, which allow to decide for some criteria that you want, in some circumstances, remove track from simulation. If during tracking kinetic energy becomes zero and there is no AtRest process, particle is killed by stepping manager. And the user can have freedom to kill any particle for any reason as well. For effective and for accurate tracking, G4 introduced conception of cutting range, which is unique for G4, is not used in any alternative Monte Carlo tools. Physically, this means we require some spatial accuracy of simulation. For example, you have interest that in your simulation, your accuracy of radiation field is of order 1 millimeter. So you have your setup, there are part of your setup which you have interest to simulate what is the radiation inside, and you want to know with accuracy 1 millimeter, for example, what happens within your radiation field. And you don't care about 1 micron distance. It is one story. Another story, if you want very detailed simulation and you want to have 1 micron accuracy of radiation effects in a given material, you may define for each G4 region what value cutting range should be used. In G4 initialization, this cutting range requirement for each geometry region transformed to production thresholds for kinetic energy of secondary particles. And you produce only particles above these thresholds. Idea is that low energy particles have ranges less than required accuracy, so no sense to produce them, better to deliver their kinetic energy at the step. Physics list. Physics list is an object that is responsible for specification of particles and physics processes. It is one of 3 mandatory objects which user need to provide to run manager. And it is, of course, a flexible way to set up physics environment, list of particles, list of physics processes. Initially in G4, we assume that each user will provide its own physics list, but very soon we understand. It was understood that it is not practical. It is more practical to take physics list from G4 sublibrary, because in that case you may compare your results to results of your colleagues, and physics lists are prepared and are used for a long time. So level of validation of physics lists, which are prepared within G4 distribution, is much more, and it is much more than any handmade physics list for users. So we call these physics lists reference physics lists. and different groups using reference physics list from G4 distribution may compare their results. This does not exclude possibility for creation of custom physics list for your application or additions of extra interaction on top of physics list which provide by distribution. In order to make this life easier, we introduce conception of modular physics list. Modular physics list allow to register physics by constructors, and each new physics constructor may implement a group of physics processes. We have types. Electromagnetic. It is basic electromagnetic interactions. Electromagnetic extra, for example, leptonuclear and neutrino nuclear. We have a module which is responsible for decay and another module for radiative decay. There are separate hadron elastic, hadron inelastic, ion elastic, ion inelastic, stopping of negatively charged particles. It is possible to add step limiters, tracking cards on top of everything. There are optical physics, which is orthogonal to any physics described above. And user may add custom constructor. In order to do this, we have stable interface G4V physics constructor, construct particle, construct process. And you may take physics list from distribution and add on top your custom physics for example, exotic particle, which is not part of standard physics list we provide in distribution. When you learn C++, there are general recommendations and rules how to instantiate physics object classes, and ownership of class and physics object is important component of all this story. In G4, it is quite complicated. We do this complicated structure in order to be effective. So it is not because we don't know C++ rule, but because we have specific simulation task. And we have physics list helper, which provide correct order of physics processes. We have this basic call register process when we take physics process and particle definition, and we include this in correct place where we may register next interaction with the next process. And if you introduce custom process or particle, you may add particle definition. You may add process to this particle or to ordinary particle. You may add, for example, discrete process, or you may add the process. The most general interface when you add a process, you give ordering parameters for AtRest, for AlongStep, for PostStep. It is not needed if you register known process to system. But for your custom, you may do these things. More simple situation, if you add discrete process, you simply add this process to process manager, and that is for case if your process active on 3 phases of step, AtRest, AlongStep, PostStep, you need to put correct ordering parameters. Ownership of classes is not belonging to physics list class. It is quite complicated to implement inside physics list class because particle definition are static and shared between sets. G4V process are registered in each thread in local store. Model classes for and process classes for electromagnetic hadronic physics may be shared between particle type, and the same process class can be belong to simultaneously to several particles. Cross sections may be shared between different particles. This sharing mechanism allows you to have say more shorter time for initialization and less memory required for the application. In order to handle all these, we use so-called registration mechanism when all cross-sections, processes, models are registered in thread local store, and store is responsible for destruction of objects. And there is important limitation that all process models and cross-sections should be instantiated with new. And then should not be destructed by a class where it is created. Everything is centralized. A few words about Gen4 initialization. We are trying to provide some service to print some information about current configuration of Gen4. We print out tables of parameters. We print out list of processes and models for selected particles, for main particles of simulation. We print separately electromagnetic hadronic. Of course, it is important information in order to understand what is used in your simulation. But when you become familiar, and many users will say, no, I don't want to see it. I trust that physics configuration is correct. In that case, all these printouts may be disabled. And for that, there are UI commands to set verbose to 0. By the way, default Gen4 physics verbose is 1. In that case, we have minimal printout information at initialization and do not have extra printout in runtime. If we put verbosity level 2, 3, or more, you may have quite a lot of very long printout information which come out from your simulation. So the optimal choice is either use by default verbose 1 or disable it with verbose 0. At initialization, we have number of UI commands which allow you to change some parameters of physics, of hadronic, electromagnetic, and you may do it before run initialize or just after run initialize before all initialization of Gen4 is finished. Few other comments. Gen4 approach for ions. As I said before, light ions are defined, and there are individual Gen4 particles, G4 deuteron, G4 triton, G4 helium-3, G4 alpha. Generic ion serves for all ions with charge above 2. Generic ion is not a real particle. It is a particle with charge +1 and proton mass. And we don't track generic ion itself, but we configure generic ion. And in that case, all other ions pick up information about processes from generic ion. What kind of ion may be? For example, C12. It is a typical ion, carbon 12 in ground state. So nucleus has zero excitation energy. But maybe some stable isotope, for example, cobalt 60 with excitation 58 and 6 keV. It is first excitation state for this isotope, cobalt 60. And in this sense, ions have unique name. And number of such ions may be about several thousand inside G4 simulation. But what about exotic particles? Not discovered particles are not part of G4 particle library. But many of you are involved in LHC experiments, and search for exotic particles is a part of physics task which you need to implement, which you need to carry out. Our recommendation that you need to define in user code additional constructor of physics, which has construct particle method. And in this method, you add exotic particles there, and you define construct process method with decay channels and interactions of this exotic particle. We don't do it because there are too many exotic particles. They have different masses, different properties, and we cannot in advance know what to put there. And very often there is a scan over masses, and all this should be in hands of experiment. But recently we introduced a new conception, which called G4 unknown particle. For this particle, we have a space holder unknown particle, but particle definition is not defined. So everything can be defined in the same way. So decay channels, ionization, multiple scattering for these particles may be used, but in tracking time, we use only dynamic particle information and don't use particle definition data. So this may make user life easier, but we are not 100% sure that this unknown particle will be useful for many applications, because we have already in LHC run 1, run 2, run 3. And there are mechanics how to define exotic particles in the experiments. We offer two extended examples, monopole and DM particle, which show tips how one can work with exotics. And it's worth to mention that in monopole example, there is special transportation, because monopole has magnetic charge and has specific trajectory in magnetic field. And the last probably The last chapter of today's talk is cuts. Cuts in range are defined for gamma, electron, positron, proton. Cut for proton is used for all hadrons and ions by elastic scattering process. It is cut on recoil ion. This cut on proton used absolutely differently from cut on gamma electron positron. For gamma electron positron, it is cut on secondary particle produced interaction. And for proton, it is limit energy threshold for recoil nucleus in any interaction. These cuts may be defined via UI command and may be changed for given setup. And there are several methods how to define cuts. In past, there was set cut method inside physics list, and it was widely used, but after migration to empty mode, this simply not optimal, but we have a list of UI commands and corresponding C++ interface which can be proposed. For example, the simplest method to define cuts is UI command run set cut and then value cut in range 0.01 millimeter. But it is possible to make a more detailed definition of cuts. For example, run set cut for a given particle type electron, 10 microns. There is also a possibility to define cut for G4 region. Run set cut for region gas detector, it is 0.1 millimeter. So everywhere will be cuts which are defined in command set cut. But for this region, cut will be different. Cuts cannot be whatever because not all physics process may be not able to work with very low cut value. And due to that, we have extra command, set low H of a cut. So default limitation is 1 keV, but you may reduce this low energy limit to whatever value you want. High energy limit cannot be above 10 GeV. Which processes use cut in range? First of all, it is not mandatory to use cuts in physics, but there are two processes where cuts are strongly needed. It is Bremsstrahlung and ionization. We also use cuts in E+ and minus pair production processes. But for a number of other processes like gamma electron interactions, we may enable cut for which is not strongly needed in order to reduce CPU, but it is little bit reduced CPU time, a little bit reduced number of secondaries. For example, if you apply cut for the electric Compton or gamma conversion. And here we repeat that there may be limits and set low H 100 keV is useful. For proton cut, we can set to 0. In that case, in each elastic interaction will be produced a recoil with maybe very low kinetic energy. And in one step, this ion will stop. But you may increase this depending on what type of simulation you are doing. Additionally, for more effective CPU point of view simulation, it is possible to introduce tracking cuts. For example, in some cases, there are unwanted particles in your simulation and you want to kill. For example, you have ordinary setup and you do not expect neutrino physics to be studied. So you may kill all neutrinos when they are produced in case of decays, semi-electronic decays. And you may add this feature to your simulation. What is included in G4 standard physics list, reference physics list? There are two things. In ionization of charged particles, there is tracking cut 1 keV, which may be reduced if needed or increased, and time cut for neutron transport, which is 10 microseconds. Again, you may change these limits depending on how your setup is working and what is your task. You may reduce or increase these thresholds. It is fully customable and can be changed via UI command or C++. Thank you.
Thank you, Vladimir. Just for people who were not looking at Mattermost, we had some problems connecting to Mattermost for a while during your talk, so I have an accumulation of questions. Some of them have to do with hadronic physics, so I will defer them to after the next talk. I'm trying to select the ones that do not. They do touch on other topics, but the first one is, if I have fluorine 18 as my primary source and generate primaries, will it decay automatically, or do I need it to explicitly register the radioactive decay process? And potentially it's AtRest ordering in the physics list.
First of all, radiative decay may be registered via a constructor which exists in distribution. There is a class, radiative decay physics, which may be added, which is added in some physics list in our distribution already, where it is. So the call of modular physics is register physics. In reference physics list, we register a number of physics processes. By default, in default physics list, which is FTFP-BERT, radiative decay is not included. But in FTFP-BERT HP, HP means high precision neutrons. In this physics list, we have radiative decay enabled. And even if default, you have your physics list, modular physics list class, you may, after instantiation of physics list, you may call register physics and add existing radiative decay physics. Radiative decay physics itself is quite a simple constructor. You may have a look into distribution, find out it, and you may see how it is done. Of course, you may do by hand the same instantiation of radiative decay. But why not to use prepared method?
I think that there was a question about optical physics. We'll leave it for the next, for this talk specific on that. Regarding, there are
regarding optical physics as well.
The dedicated talk or two, so it's fine. We'll discuss it then. Is there a way to check the emission spectrum regarding ion tables used in G4? Is there a way we can check the emission spectrum, for example, betas and their probability used as input?
There are examples for examples extended radiative decay, which allow to study what is inside Gen4 for radiative decay. And these examples are really useful, and we have a discussion with users about quality of this simulation. It may include also beta decay, maybe alpha decay, whatever. What is inside Gen4 for given isotope you have interest to, you may study this in simple way, and then use in your full simulation.
The follow-up was whether it applies for Auger electrons or internal conversion electrons apart from simple betas. I think that simply put, you can look at the relevant example.
We have internal conversion. In past, internal conversions should be, in past we proposed always to set a flag, I want to have internal conversion. But with time we come to solutions that if we let's define this internal conversion by default. So in default variant, we enable internal conversion probability.
Then the next question regarding a person who's interested only in the simulation of muons, basically. They of course list what are the relevant processes. The question is, can you use one of the predefined physics lists or create a custom one by registering only EM standard physics option 4? I guess this will be answered by physics list, but you can give a quick answer, which is basically that's included.
Please repeat the question. The question is muonic atom or what?
No, just muon physics.
Muon physics is inside each physics list, each standard physics list.
I'll refer the questions about their accuracy to the electromagnetic physics talk tomorrow.
Accuracy, of course, depends on type of physics list, but for main HEP applications, default physics list has decent accuracy.
There was a question more about ions. Does the Gen4 helium-3 and alpha represent the ions fully stripped, or can one change ionization states?
We have currently in sector of Gen4 DNA, we have processes decrease and increase the charge, and we can change charge state of given ion. By interface, it is possible. But this simulation is specific because you need to have cross-section of such process. For Gen4 DNA domain, there are information, there are cross-sections for change charge. And for other materials, we do not have yet released this probability of charge exchange. It depends, of course, on media where the track is going.
Okay, thank you. There's a group of questions about multiple scattering. I think probably best to discuss them tomorrow, because I don't remember how much multiple scattering features in the EM physics talk. My memory is that it does.
Yes, according to time, I may answer something if we have time. If I not take too much time for this talk, I probably will stop sharing.
Yeah, I think we do need to move on to the next talk, but very quickly, one of the questions is it appropriate to use Pythio or MadGraph-like event generators coupled with Gen4 to study the detector response? to any user-defined particles? I think that it depends on what you're discussing. If it's exotic particles, then I'm not sure that how many of, well, they probably will have some of these, but not interaction with nuclei, interaction with
Yes, there is an example in preparation, not yet released, which shows how to use an Monte Carlo event generator, like PTIA, for instance, for specific interaction happening at the level of detector simulation. For instance, to have a more accurate gamma nuclear simulation than what you have in Gen4, for instance. So it's possible, it's not trivial, but there will be, hopefully at the next release, an example showing how to do that.
Yes, for example, all details of tau decays may be used through these generators, through external generators.
Okay, thank you very much, Vladimir. I think we'll move on to the next one. If we did cover the talk, we didn't cover the question, and they are not part of any previous, any part of known sessions, then we will, there are other opportunities to raise them. Sorry, I need to share here again. And I need to stop and start recording, so please excuse 1 minute.